In this video, we're going to cover section 1.6.1, rate determining steps. Now, as we saw in the previous video on sequential first-order reactions, the rate of product formation in a sequential reaction is dependent upon the timescale for formation and decay of that intermediate species. So as a result, we can envision two limiting situations as a result of these differences in the timescales, that is, the rate constant with respect to the formation of the intermediate and the rate constant with respect to the decay of that intermediate. So the first limit is where the rate constant for the intermediate decay, that is K2, is much greater than the rate constant for the production of that intermediate. So we could show that particular condition or limit as K2 is much greater than K1. So in this limit, any intermediate that is formed will rapidly go and be transformed into a product. And so the rate of product formation depends on the rate of reactant decay and not on the rate of the intermediate decaying to product. So again, if this rate constant is really large in magnitude relative to the magnitude of K1, as soon as A decays to I, it goes to product. There's no buildup of the intermediate concentration under that particular limit. Now, the second limit would be the opposite scenario. So the second limit occurs when the rate constant for intermediate formation is significantly greater than the intermediate decay rate constant. So that is, K1 is much greater than K2. And so in this limit, the reactants quickly produce the intermediate, I, but the rate of product formation depends solely, in many ways, on the rate of this intermediate decaying via K2. And so it doesn't depend on the decay of A to I, but depends upon the decay of I to P. So therefore, the rate constant K2 is more relevant in a sense because its magnitude is lower. So these two limits give rise to one of the most important approximations made in the analysis of kinetic problems. That is the rate determining step. Which step in a particular mechanism, in a sense, determines the overall rate of product formation. So the central idea behind this approximation is the following. If one step in the sequential reaction is much slower than any other step, then this slow step will control the rate of product formation and is therefore the rate determining step. So let's consider again the following sequential reaction, where we have A decaying to the intermediate I, which then further decays to give us the product P. So under the limit where K1 is much greater than K2, the elementary step corresponding to the decay of I is the rate determining step. So again, because K1 is much larger in magnitude, we're going to see the decay of A to I being much more rapid, occur much more quickly than the intermediate decaying to product. So therefore, K2 becomes the rate constant of the most important step, if you will, or rate determining step in this particular sequence. So because of that, if K1 is much greater than K2, so K1 is a much larger value, if we look at K1 in the exponential term, if this K1 value is much larger, e to the minus of a much larger number, that particular solution is going to be a much smaller value than e to the minus of a smaller magnitude of rate constant. So if we look at our expression for the concentration of product, we saw that it was dependent upon various terms. And we can simplify this now, because if K1 is much greater than K2, then this term here is going to be relatively small. We'll say it goes to 0 with time, but it's going to be a much smaller value. And similarly, e to the minus k1t, we said, will be a much smaller value as well. So this will also, in a sense, decay to 0. And so under this condition, under this limit, we see a reduction in what appears to be a more complex expression for the product concentration. We see that to simplify quite nicely in that we have minus k1 on the bottom can divide into the top, so we lose our k1s. And so we're left with 1 minus e to the minus k2t. And again, because the product concentration is expressed in terms of, if you will, the only rate constant in this expression being K2, that in its sense tells us that K2 is the rate determining step because it determines the overall product concentration. So in summary, the time dependence of the concentration of the product when K2 is the rate determining step is identical to that predicted for the first order decay of the intermediate, resulting in product formation. And we saw this previously with first order rate laws, that the concentration of the product was in fact equal to the same expression, where K2 was the rate constant for that step. So given that K2 is the rate constant in this expression, that coincides with the limit that K2 is the rate determining step in this particular sequence of reactions. Now we can look at the other limit, that is K2 is much greater than K1. So in this scenario, the elementary step corresponding to the decay of A is the rate determining step. And so if we carry out the same simplification, we can state again that K2 being much greater than K1, that results in the exponential term e to the minus K2t being a much smaller value than e to the minus K1t. And so again, we can simplify our particular expression. So K2 being much greater than K1, K1 is going to be considered a very small value relative to K2. And as a result, e to the minus K1t will also be much greater than e to the minus K2t. So e to the minus K2t, that is also going to be a relatively small term, and so is the product with K1. So that whole term drops off. And what you're left with is minus K2 e to the minus K1t all over K2. So K2 will cancel, and you'll be left with 1 minus e to the minus K1t, all multiplied by the initial concentration of A. So in a similar way, the time dependence of the product concentration when K1 is the rate determining step, this is identical to that predicted for the first order decay of A, resulting in product formation. So a good question to ask oneself is, when is it appropriate to use this approximation, this rate determining step approximation? And so the general rule of thumb is that for a two-step reaction, as in this example, a 20-fold difference between the magnitude of the two rate constants is sufficient to ensure that the rate constant of smaller magnitude will be rate determining. So if we have that 20-fold difference between K1 and K2, as we saw in this example, that's sufficient to ensure that we can invoke this particular limit or condition and allow us to calculate with fairly good accuracy what the concentration of the product is, being that we know what the rate determining step is in that two-step sequence. Now, another way we can look at this rate determining step approximation is its relationship to the activation energy in a particular scheme. And so for this scheme, where we have the reactant decaying to some intermediate I1, and then this intermediate being transformed into I2 before forming product P, we can also relate the rate determining step to the step that has the highest activation energy. And we use the Arrhenius expression to show that, and we'll discuss that in later videos. But for our purposes at this point, we know that the rate constant is equal to a pre-exponential factor multiplied by e to the minus EA over RT. And so it goes to show that if you have a very large activation energy, e to the minus EA over RT, where EA is a very large value, e to the minus of a large value is going to be a very small value multiplied by that pre-exponential factor. And so the rate constant will be quite low in magnitude if you have a very high EA. And the opposite is true, that if you have a very small activation energy, you'd expect that the rate constant for that elementary step, the magnitude of that rate constant would be quite high. So this step from reactant A to the intermediate I1, this step having the rate constant with the smallest magnitude, this will be your rate determining step. And so the rate determining step will have the highest activation energy. And then steps of larger magnitude will have lower activation barriers, as shown in this example. So if you have any questions about this approximation, that is the rate determining step approximation, any questions about how we derive those equalities for the product concentration, or our preliminary discussion on the, correlation of rate constants, the magnitude of those rate constants with activation energies, by all means, send me an email and we can have a discussion about that on the Zoom platform. Thank you.